fine tune and make sure that those decisions are implemented to the level of satisfaction. Now, intelligent. So therefore, if a building or any or robot or anything to be intelligent, it should be processing information, making decisions on its own, and implement those decisions. You can see now, when it comes to information coming from the senses, right? For example, humans have five senses. We collect information from five senses, process them, and understand them, interpret, right? And then implement, make some decisions, and then implement those decisions. For example, a security officer sitting at the main entrance, right, sees somebody, a visitor coming. His vision, the senses capture the image, and those images are transmitted, communicated to the brain, and the brain processes the information and makes a decision. For example, open the gate or say, no, you are not allowed to enter this building, something like that. And so it's intelligent. Now, if the building is intelligent, for example, if building has intelligent access control system, the building, without needing a security officer, should be able to do the same. Use a camera, right, and capture the information, send that information to a computer. The computer uses software to process that information, the image, and then identify the person, makes a decision, right, whether this person is allowed to enter the building or not. So you can see, therefore, you need a processor necessarily, a brain. For example, in an artificial system like intelligent building or a robot, the brain is a digital computer. We know that if you look at even human, right, the brain is cannot do much if the brain is not trained. That is why the parents send children to the school, education, right, to install the software. It's like computer without software is like a brain without education and training. It cannot do much. It cannot do many things. It cannot make decisions, smart decisions, right? So therefore, we can see in an intelligent building, there must be sensors collecting various information, okay? There can be thousands of them working with the air conditioning systems, lighting control systems, access control, fire and safety, and so on and so forth. And then computers processing this information, transmission, data transmission, set networks, transmitting this information to the computers. Computers to process this information computers need software, otherwise cannot do anything. And then software, okay, building analytic software in the computers processing the information, and then the interpreting the information, the results, and then making decisions and communicating those decisions to various motors, valves, and various other actuators. For example, open the door, the computer issues a command to the door motor control to turn the motor so that the door is open. Okay, right. Now, the thing is, a building can be intelligent in numerous ways. Now, if you look at access control system, nowadays it's very straightforward. Fingerprints or face recognition, you know that these technologies has come long way. You can imagine how powerful the face recognition algorithms the Mark Zuckerberg's Facebook is using. How many users, but still the Facebook face recognition can recognize people to great accuracy. So then implementing access control system is very straightforward. It's not difficult nowadays. The technology has come to a point that implementing such systems easy. If we look at another example, such as maybe smart lighting control system, for example, in a given indoor space, right? you have a smart lighting control system. That means you have sensors inside to detect the light intensity levels indoor, and then to check the occupancy, use occupancy sensors to check whether there are people, which part of the building the people are, and check the daylight availability, right, with some sensors mounted outside the building. And this communi- computer reading this information make decisions. For example, the computer decides to turn off some of the lights and open the blinds. You know what I mean? You can have glasses, the, the partition walls. You can have the glasses. You can computer can communicate with blinds. You know what I mean? Blinds, right? Open and close like this to allow daylight, right? Motorized blinds. Motorized means controlled by a motor, and the computer communicates with the motor and you know opens the blinds, allow daylight to come in, and then allow daylight to come in, and then turn off some lights and dim the lights, some of the lights, and so that way, um, fully automatic. There's no human intervention. The building itself intelligent, and that way it saves energy, right? Without compromising the user comfort. The light level required in the indoor space is maintained. There's no compromise, but it saves energy. So it's a smart lighting control system. Now, and also it knows the light intensity at the office, light intensity at a meeting room, in a theater. It knows the standard light level required. The software knows it. But today I'm not going to talk about access control or interior lighting system or maybe um, energy efficient mechanical transportation system, right? Because these technologies are relatively straightforward, given the advanced technologies available nowadays. If you look at undergraduate student at the Department of Electrical Engineering will implement such a system. So instead, today I'm particularly going to talk about HVAC, because HVAC consumes lots of energy. Some 30 to 40% of the energy in many buildings, HVAC systems responsible. Um, at the same time, the intelligent um, HVAC system, there are lots of things involved in there. So it's a little complex compared to other systems. So as a result, because HVAC contributes to the how green the building is, how energy efficient the building is, right? How environmentally friendly the building is. At the same time, HVAC system in a smart building is not very straightforward. There are lots of things involved. So I pay special attention to that part of a smart building today. Now, okay, these slides, oh, slides don't move. How do I move these slides? It's so long. Okay, there we go. These are some slides that I use when I make presentations overseas. Some nice pictures, right? This is Sri Lanka. So I show them when I make presentations overseas. Okay, um, right. Um, this I would like to show. You can see the effects of global warming, right? Melting ice, glaciers, causing the water levels in the seas to go up. You can see what happened last year, August. 12.5 billion ice melted because of global warming. The energy and buildings contribute a lot because most of the energy production generation methods are environmentally unfriendly. And if you can save energy, right, in the buildings can operate with minimum amount of energy. That is very important for that building to be able to, for us to call it a green building. Now, um, okay, so last year, February, Green Building Council Indonesia published this result. They conducted, in collaboration with the World Bank, they conducted a study. They took into account 9 green certified buildings in Jakarta, and they compared the resource, energy and other water, the resource consumption of these green certified buildings with their standard buildings, right? Non-green certified counterparts in Jakarta. And then they found out that these green certified buildings give 30 to 80%. You can see how much it can be, 30 to 80% of annual utility costs. There are lots of examples, lots of practical examples. So, 40%, 60%, and so on. And one important point here is additional cost of 0 to 17%, right? This is very important. 0%, that means with no additional investment, you can gain something like 30 20, right? How? By just being resource conscious, energy conscious during the design phase of the building. So number one, architectural design. Number two, civil engineering design, particularly, right, not only the orientation of the building envelope, but particularly the material. So thermal design of the building, design the building so that thermal losses are minimum, right? And it's possible. What is this 0? I'm really keen on this 0 rather than 17. 0 means by ensuring, energy-based, energy-conscious architectural and civil engineering design without any additional extra investment, you can save a lot. 17%, if you spend this 70% of the construction cost of the building, if you invest, you can go as far as 80% of savings. Here you're talking about utility bills, water, gas, everything, right? In many countries, the buildings accounts for 30%, the total energy consumption. Sometimes can be 40% in many, many countries, right? Buildings can be residential, commercial, industrial buildings, right? So that's why I told Ceylon Electricity Board recently, look, save energy in these buildings, don't give permission, don't give supply if they do not, satisfy the thermal design requirements, specifications, right? That way you save energy. Right? If you can save 30%, forget about 80%. 30% into 30% is almost 10%. You can shut down some power plants instead of talking about constructing new power plants. So this is the kind of difference you can make. Why it is important, the resources, energy, all the resources coming from, the environment, from the earth mainly, and particularly producing electricity is not environmentally friendly. We have to use mostly environmentally damaging methods to produce electricity. All right, let's move on. Now, if you look at a building, this is how it looks like, but we don't see, the hidden behind the scene. There are lots of electronics. The electronics related to components, sensors, communication devices, right? Power, processors, okay, motors, right? Motors working with pumps, fans, compressors, elevators, etc., etc. And these things um, you can see, right? Monitoring, okay, and you can monitor through a cloud. You can completely monitor the building from a distance, from completely different countries sometimes. The performance, the technology has come a long way. Now we are talking about building Internet of Things. We're familiar with Internet of Things, lots of devices interconnected, and then in large commercial buildings, you know how large today's commercial buildings are. There are so many hardware components, devices, lots of interconnections. Now there's a field called building Internet of Things, building Internet of Things, BIoT. So that there's a testimony for how far the technology has come. Now we look at the green building. The definition is environmentally responsible and resource efficient. Because if it's resource efficient, definitely it is environmentally responsible because the resources coming from the environment, the processing of these resources, etc., often environmental damaging. Transportation, right? So basically, um, the sustainability, we talk about sustainability means is think about tomorrow. That means meet today's requirements without compromising the ability of the future generations to meet their needs. That's sustainability. It's like you think about your children, right? You think about tomorrow. It's just we don't finish it off everything today. Now, now, okay. So the artificial intelligence has come a long way. This is when a computer defeated world chess champion 1997, way back in 1997, right? Actually, later turned out that you don't need much artificial intelligence, the processing power. The computer processing power and the software can make very smart things. This is computer defeating the Go, the world champion, right? Go is a board game. It's right, temperature, pressure, whatever. You need software. That's pretty clear to implement decisions, opening a door, speed up fan, speed up compressor. You need motors. You need valves and solenoids, etc. The computer communicates with the sensors and these things to implement, right? And then you need communication to interconnect them. Communication network, wired and wireless, right? So it's like you have various different types of building services, all different types. Building services, fully automatically, right? Operated, managed, monitored, right? Controlled by digital computers. You can have more than one, right? Computers looking after fire, computers looking after security systems, are dedicated brains. Now, as I mentioned, my special emphasis is on HVAC. Okay, we have already spent 20 minutes, and you can imagine if you look at the defense headquarters HVAC system, for instance, you're talking about 205 air handling units. That's where the air is treated, right? In a air handling, air conditioning system. 200 direct digital control panels, right? 10,000 hardware points. When you say hardware points, sensors, communication devices, processors, various actuators. Now, this is the thing, as I mentioned, in many countries, 30, 40%, right? Energy consumption responsible, the buildings responsible, and then HVAC, again, about 30%, 40% in a lot of commercial buildings, right? And we know that savings possible. Now, basically, in today's lecture, we are going to look at how to go up to 80%, right? That 30% saving that Indonesia Green Building Council example can be achieved by simple architectural design and civil engineering design, right? Make sure that your walls um, are thermally insulated so that the air conditioning is not lost, right? There are no heat creepages, heat leaks, etc. But if you want to go to 80% level, you have to do a lot. That is what we're going to talk about today, right? How to go to as deep as 80% savings in a building. You have to do much more than architectural design and civil engineering design. Now, if you look at HVAC system, these are the energy consuming elements. Compressors, right? With the chillers, pumps, fans, the condensers, in the cooling towers, etc. There are the tiny devices like damp actuators and so on, right? Now, here we are talking about saving energy without compromising the user safety and comfort. There's no compromise the comfort and safety of the user. Okay, that means if you turn on the AC and live inside the building with utter discomfort, right, your productivity will be affected badly. It's not a green building. Green building does not compromise safety or comfort, right? These are the American Society, the Heat, Refrigeration, Air Conditioning Engineers Society, the standards. Okay, you can see even the air velocity is defined. The person inside the building should not hear the sound of the fans and should not feel the air motion. Okay, now you can see cooling towers, the top of the buildings, right? And in here. Now this is how it works. Now you have chiller. Chiller produces chilled water. The chilled water is pumped. You need pumps, right? Pumps are pumped to air handling unit. This is where air is treated. This air handling unit is taking care of this indoor space. This air handling unit taking care of this, and so there can be hundreds of them in a building. Let's say a hotel, right? Now, and then this chilled water goes through the cooling coils of the air handling units and then cools down the air. That means basically the heat in the air is absorbed to this water. It comes back. It comes back. The chiller has to cool it down and send back at a lower temperature. Okay. And the chiller is a refrigerator, basically. It's a refrigerator that produces chilled water. Okay. There's a refrigeration cycle going, and then the refrigerant, to cool down the refrigerant, you know that if you go close to your refrigerator, particularly the backside of the refrigerator at home, you will feel it's very warm out there, because that is where the hot refrigerant in the refrigeration cycle is cooled down at the condenser. Here, the condenser we're talking about is a water cooling system. It has a water cooling system. This water is called condenser water. The condenser water is supplied by cooling tower, right? Condenser water comes in. You need again motors to circulate them, goes through, absorbs heat from the refrigerant, goes back to the cooling tower. Cooling tower uses large fans to cool this water down, and the supply condenser water at a constant temperature. Just like this supplies chill water at constant temperature. Okay. So the thing is, if there are lots of people in this space, let's say lots of people in this space, there are lots of heat to remove. When there's a lot of heat to remove, this water will flow very fast. The flow rate, right? Cubic meters per minute will be higher. If the amount of heat to be removed is high, we say the heat load, thermal load is high, right? And then these pumps will work fast. The compressor here, the chiller, will have to work fast, right? More refrigeration cycles per minute. And they have to work fast also because a lot of heat to be removed here. So then this water has to run faster. These pumps will work fast. That means here there's a cooling job to be done, cool down the condenser water. The fans in here will have to work faster. So you can see there's more heat to be removed, more work for the fans, pumps, and compressors. Okay. Now the question is how to achieve that 80%. That is the question. All right. Now, if you go to the fundamentals, the working principle, I think we need to understand that. This is what happens. Okay, you have the cooling coils inside the air handler unit. You have air circulation fans, air filter sends through the cooling coil. Let's forget about the heating for the time being. It's cooling. Okay, and then since these circulation fans takes the warm air from the room, sends filters, sends through cooling coils, and then back to the room, right? And then the user, the occupant in the room can set the temperature. Right? You can see there's a controller. Controller receives the temperature information from room 2, from room 1, and then it opens and closes the air supply dampers. When this dampers in the air ducts open and close, right, depending on the flow rate requirement, this fan speed goes up and down, right? If the damp opens, this fan goes up speed, right? And sending more air, the more air per minute through the coils, cooling coil. The chill water flows through these cooling coils, all right? Yeah, coming in, low temperature, absorbs heat, goes back. It's like a radiator in a car. Now, it's different, but it does the same job. Now, what happens here is there's a temperature control. Now, this kind of temperature control happens here. Now, there's a sensor, right, to detect the discharged air temperature, right? The sensor feedback to the controller. Controller knows the set temperature by the user. You set the temperature, right? For example, you use this to set the temperature. Controller knows the temperature you're looking for. It compares the set temperature with the actual temperature. And let's say the actual temperature is higher than the set temperature. The controller, the brain, communicates to the valve, chill water valve, right? There's a motor, communicates with the motor power supply, and then voltage is decreased or increased, and then valve is open, allowing more water. When the valve is open, you know, they're going to be a static pressure difference, pressure change in the water supply circuit, the water circuit. And then when that happens, okay, the pumps, chill water pumps speed goes up, right? So that when the valve is open, that means more chill water per minute. That's a sort of a signal. And the pump speed goes up, and then pumps going to, because when you open the valve, the friction, right, the head decreases, and then the flow increases, okay? If you're familiar with these pumps, how they work. So there is a temperature control problem here. You can see air temperature control, right? temperature control problem 1. And there's a speed control problem, fan speed control, right? Fan speed control problem. 2, adjust the flow rate, air flow rate. Okay. And then when the valves open, the pumps, chilled water pumps speed goes up. So there's a pump speed control. Whether it's a fan or a pump or compressor, all these are called turbo machineries, are powered by motors. Basically, your computers communicating with the motor controls. Every motor has a control, right? Controllers. Now, refrigerator, right? Chiller. Chiller is a refrigeration cycle. You know that with the evaporator, this is where the chilled water is produced. Warmer chilled water comes in from the air handling units. Refrigeration cycle happening just like the same principle as the refrigerator at your home, cool down, right? And this temperature, this chiller has to maintain this temperature at constant level all the time. You understand that if the heating load is high, this water, because the pumps run at a higher speed, this water will flow faster. It doesn't matter, it can be slow, fast, how fast, it doesn't matter. This system has to maintain the supply chilled water temperature at a constant value, constant temperature. So therefore, there's another temperature control problem here. Temperature control problem 2, right? That is the control the temperature of the chilled water. All right. Now, this refrigerant absorbs heat, goes to it evaporates. The vapor form goes to compressor seat. During the compression process, the temperature goes up according to the Boyle's law. You know that when you decrease the volume of gas, the temperature goes up, right? So in a liquid form, mostly liquid form, hot is hot, comes out, liquid form to the condenser. Condenser has to cool this down, right? It uses water circuit again. It's a water cooling, right? And this is the condenser water. Cooler the condenser water comes in. It cools down the refrigerant, and warmer condenser water goes back to the cooling tower. You can see a cooling tower. There's a cooling tower. It's cooling towers, right? Condenser water is cooled down here. And then this cooling tower has supplied condenser water at constant temperature. That means there's a temperature control problem here. Temperature control problem number 3, right? There are 2 speed control problems: fan speed, chilled water pump speed control, and the compressor. There's another speed control problem, number 4. And then condenser water pumps, you need pumps to circulate this water. Condenser water pump speed control problems. Now, you can save energy everywhere if you do it very, very smart way, right? Careful design, and go to the very depth of it and tune to the maximum you got to do if you want to achieve that 80%. All right. Okay. Now, this thing, what are the technologies used to achieve that 80%? Instead of use variable frequency drives, that is, you have the motors working with fans, pumps, right? And compressors, right? So variable speed drive means these are outdated, 20 years old outdated things. Let's say you want to control the flow. You have a motor, you have a pump, you have a throttle valve. You open, close the throttle valve to control the flow. Then what happens is the pump pushes the water. This water is hitting the valve. Loss of energy is wasted here, right? Because it's the valve that is controlling the flow. Pump is running at a constant speed, rated speed. The pump, whatever the flow is, output, the pump energy consumption is a constant. And it's a waste. The thing is, the torque is proportional to the speed squared, speed rather. Hold on a second. speed squared, right? The flow rate is proportional to the speed of the pump, and speed of the pump means speed of the motor, and the power is the torque into speed, basically, right? Power is torque into speed. Is the torque proportional to speed squared, and the power speed Q, you can see. So this power, right? The power is supplied by the motor proportional to speed Q. Now this is running at a constant speed, this system. So that means all the times constant speed. But if you remove this valve and if you use electronics to control the motor, right, and use speed control, it's called VFD, variable frequency drive. When you want to reduce the flow, you reduce the speed. When you reduce the speed, the power reduces, right? Is cube. If you halve the speed, power becomes 1/8. You can reduce the power 8 times by reducing the speed 50%. You get my point, right? Now these are some simple examples. Now this is not water flow. This is air flow. You may have seen these things. This is variable vane, inlet vane, dampers, right? Just like a valve controlling the flow here, the fan is running at a constant speed, motor is running at a constant speed. You open and close these damper, these flaps to control the flow. So what happens is air is coming and hitting here is an energy loss, right? So instead, you can use VFD. This is a commercial VFD. It's electronic. It's fully electronically controlled. You remove this as much as possible. You remove the valves and the dampers, and try to do it with variable speed controls. So basically, you replace the VIV dampers, damper motors. You can also remove damper motors because dampers need motors. You replace the regular motor fans with class F motor fans. They can run at a high frequency, right? It's called, you need class F insulation level. Now, electronics and controls, there is some investment because this you need to invest, but these things are becoming cheaper and cheaper. This way, what you do is you control the flow by adjusting the speed, and then you save power. That's a right. For example, this thing can, for example, uh, some values, but I have only 20 minutes, so I got to move fast. In kind of example, because you can see, we go with VFD, constant speed drives, right? Variable frequency drives. Not only you're saving energy, therefore the payback, 3 years payback period of for the investment, right? By saving the energy bill, electricity bill, you can see it happens in many ways. Even the size of the fan motor is reduced. 75 horsepower supply fan, now you only need 50 horsepower, right? 40 horsepower return fan, we need only 25 horsepower. This is quite similar to using VFD in the refrigerator. Now you know that if you go to an electronics shop and uh, to purchase a refrigerator, you have classical refrigerators. I'm talking about domestic refrigerator. Classical refrigerator means on off, right? The your fans and the compressor on off. It's on off. And now, but if you go for example, if you go for an inverter refrigerator means it's VFD. It's VFD. There's a VFD. The inverter is the heart of the VFD system, right? So you save energy due to many reasons. One reason is your compressor will be smaller. In a VFD domestic refrigerator, you'll have a smaller compressor than classical on-off type thing. There's energy saving there as well. Okay, this is another example. Let's take a look at this, and assume you have 3 cooling towers. Okay, just a simple example. Each powered with the centrifugal fan. I'm talking about cooling tower. Yeah, this cooling tower. You can see there's a large induction motor and a fan. Okay. Let's say there are 3 of them connected in parallel. Okay. You have 3 because at full load, 2 cooling towers operated at rated flow. Rated means 100%, right? Maximum continuous rating. You have the third one just to keep it standby. You don't use the third one basically. You keep it standby. Okay. You don't use variable speed drive. It's constant speed, or maybe a flow throttling, some sort of arrangement, or maybe there are on-off sort of arrangement. You on, off, just like a refrigerator is doing in the classical refrigerators. Now, instead of running, constant speed and 2 cooling towers to meet the full load, right, at rated speed, what you do is you retrofit this system with VFDs, right? Instead of using 2, keeping 1 standby, you run all of them, but at 2/3 of the rated flow. Or in other words, 2/3 of the speed, because the flow proportional to the speed, right? Previously, you ran 2 at full speed. Now you run 3 at 2/3 of the speed. This is what happens. Now, before, 2 fans, full rate. Let's say full means 100 or 1. You can say full means rated. I say, 100%. 1, let's call it 1. 1 into 2, because there are 2 cooling towers, right? This is the cooling effort. Cooling effort is 1 into 2, 2, right? The flow, the cooling effort. The output horsepower, 1 to the power 3, because the speed is 1 or 100%. There are 2 of them, 2. Now, instead of that, you use all 3 at 2/3 of the speed. Now, the airflow, right? The cooling effort is 2/3 into 3 is 2. It's the same cooling effort. So therefore, the cooling job will be done, right? The cooling job will be satisfied. So because the same airflow, the cooling will happen. But look at the horsepower. 2/3 to the power 3 into 3, right? The ratio 2.25 to 1 is more than 50% saving. Okay, so this is simple method. Now, what is happening in building analytics software? Then we know that this is just a simple example, just 3 cooling towers, but you have, when it comes to now, there can be large number. It's not 3. It can be 20, right? Fans, pumps in one system, and so what happens is there's some mathematics going on. It's something like, okay, let's take an example 3 cooling tower case. Assume they are not identical, or you're going to adjust the speeds. The software is going to adjust the speeds. We know that the power, the total power, there are 3 of them. First one, right? Speed to the power 3, speed n1, second one speed n2 to the power 3, third one speed n3 to the power 3. Right? They can be constant coming up, but now the power is basically first one speed to the power 3, speed of the second one to the power 3, third one power 3. And then at the rated load, the speed should be 200, right? This means 2 rated, 200, or you can say 2. 2 means you need 2 of them at the rated speed. That means speed 1, 2, 3, the sum should be 200. To meet the cooling load, or to do the cooling job, you have to satisfy this constraint. And at the same time, let's say you should not speed up these fans beyond the rated speed. This is the rated speed. You don't speed up beyond the rated speed. You can speed up beyond the rated speed if you have high frequency motor drives and special class F type, right? Whatever that is, these are constant. This is to protect the motor and the fan mechanically. This is to meet the cooling load, cooling job, right? You, while subject to these constraints, while satisfying these conditions, you minimize this function. That is the job. You adjust N1, N2, N3 so that this condition is satisfied without violating this, so that this is minimized. Simply speaking, right, you can come up with two-dimensional function. Partial derivative should be 0 at the minimum point. Okay, there is some maths. I'm not going to go into details of these things, but there are optimization algorithms there. You have a minimum point somewhere. Okay. Now, the thing is, in a real system, you can have large numbers, not 1, 2, 3, large number of them. Okay, so it's a multi-dimensional optimization problem, and the software, these are well-known techniques that are applied in here. But you have to go further. Just adjusting the speed is not sufficient, because if you look at, for example, pump, the efficiency curve, has, unfortunately, this kind of a scenario. This is the pressure or the head of the pump. This is the floor, right? It's not flat. Because it's not flat, you can see if you stay here, the efficiency is 75%. That means 25% of the electric energy input is wasted. Anyway, wasted. Can't help. But if you operate off this point, off design, somewhere here, 50%. 50% means 50% of the electricity you supply to your pump is wasted inside the pump. You cannot achieve the 80%, that thing, right? 80% saving that we are talking about. You have to do maximum and try to stay here. This is the operating point, right? This is the pump curve, pump flow. When the flow increases, pressure capability drops. This is the system curve. Right? System curve shifts depending on the load. When the valve is open in the chilled water circuit, for example, right, the head changes, system curve changes. You're operating here, efficiency 75%. When system curve changes, this is your new operating point, and your efficiency will be much, much lower. You got to do something. Software has to do something. So what does it do? One of the methods it uses, it uses parallel pumps and series pumps, right? Let's say you have one pump, two pumps. If they are connected in parallel, this is the parallel combination. It's a different curve. If you connect them in series, it shifts this way. The pressure capability increases. This is the series combination of two pumps. Two pumps, individual, series combination, parallel combination. So what you do is, when the system curve changes, you change the pump curve also. And you look for this best operating point, best efficiency point. That's what you do, the software do, right? You get my point. So therefore, what are the methods that are used? Instead of using large pumps, you use parallel pumps, parallel compressors. Instead of using one large compressor, use parallel combination so that software can switch, right? And decide the combination, the optimal, what you call deployment plan and operating point, so that efficiency, the energy waste is minimum, right? Is minimized as much as possible. And you need software, you need sensors, you need controls, you need special design. And you can see that is why that 17%, Indonesia case, 0 to 17%, you need investment there, right? You need to do a lot now. If you want to achieve that 80% of savings. So that means your optimization problem becomes 6-dimensional. Not only the speed, you have to adjust the efficiencies. It's a 6-dimensional. So you need, right, advanced algorithms. If you're familiar with, they have come a long way. Genetic algorithms, there are different search algorithms, etc. that can optimize this kind of function. That's some mathematics for a change. Okay, so basically remove the dams and valves as much as possible in the design. Most of that, all of that, before all these, achieve optimum thermal insulation. If you're civil engineering, the walls are leaking heat, right? These pumps, fans, and compressors will work and work and work to remove the heat leakages. That is unfair. I mean, no point talking about this stuff if your building is poorly thermally designed. So the architectural design and civil engineering design comes first and second, and then this to go further and further to achieve more and more. Use parallel configurations, etc. Got to use the efficiency curves to go to the very depth, right? That is what software does. Software controls all these. And furthermore, all right, I have 7 minutes. Um, you know, we know that there are time of use tariff. In addition to that, load shifting, pre-cooling, there are various techniques used, right? For example, early in the morning, electricity bill is low, right? Electricity charge is low. So then what you can do is you can, do some cooling, the chill water production earlier, right? When the electricity bill is low, you can do something like this. And this is called thermal storage. You have an ice tank, right? This is the chiller. Now this is like battery and an engine in your hybrid vehicle. Your hybrid car has a battery, motor, and an engine. The chiller is like the engine, the ice tank. So what happens is when the electricity is cheaper, right here, after 10:30, electricity is very, very cheap. When electricity is cheap, what it do is chiller produces ice and stores in the tank. Now, the hot, warm, chilled water, right, goes through this. Because it goes through this, the load, cooling load on the chiller will be lesser, just like the workload on the engine of your hybrid car will be lesser because there's a battery and you have a motor. And your electric car, the battery can be charged after 10:30 when electricity is cheap. You get my point. So these are called thermal storage. So there are lots of other things that can be done like this. So this way you can save energy, the time of use thing. At the same time, you can cut off the peak. You know that Ceylon electricity board charges for the peak maximum demand charge. You can flatten your demand curve by flattening. You can, so it's basically, it's a demand response thing. Okay, you reschedule your electric power loads to minimize the energy. And one thing is, it's also environmentally friendly because early in the morning when the load is very low, people are fast asleep, right? All the refrigerators, right? The doors are closed and no TVs are working. People fast asleep. The electricity demand is low. So mostly during this time, the electricity demand is met by hydropower, not by coal. Coal is environmentally relatively unfriendly, right? So and cheaper, more environmentally friendly methods. So that is why it's cheap. And it's environmentally friendly again. All right, so again, implementing, now you can, now much easier because today the technologies such as Internet of Things, cloud computing is, cloud computing is what we call is a computing utility. Computing utility means it can process your data, right? Store your data, manage your data, and make the data available for the energy manager or the facilities manager of the building to monitor the performance, energy performance and operational performance of the building, right? In a very user-friendly interface like this. This kind of a thing is called energy dashboard, right? Energy dashboard. Your energy manager, the facilities manager doesn't have to be in the building. I know that, for example, I know I met somebody who takes care of the buildings in London, the buildings in Italy. His company and they are in London. But you don't have to be inside the building because you get all the information through the cloud. The cloud is basically internet. It's a large database, right? You are connected. Okay, you're building devices, everything's connected. You don't have to be in the building to receive this information. Okay, so therefore the technology has made technology is available. Basically, it's a decision. All right. I think yeah. So I hope we can spend few minutes. It doesn't matter as long as Situmini allows for a discussion. If you have any questions, we can discuss. Please feel free to ask questions or make comments. Basically, in today's lecture, I wanted to highlight how to achieve this much. So therefore, green building is not something, with a lot of trees and vertical garden. That's not enough. And you can do a lot more. That is the purpose of my lecture. I wanted to show that there's a lot more that can be done. And if you do the maximum, you can go as far as, there are examples, 60%, 70%, 80% can be tough, but be careful, design from the drawing board, from the very initial meeting, has to happen in an energy resource optimal design. It's not only design, operation, controls, maintenance. So when it's an intelligent building, it's not only this. When it comes to intelligent building, you can make the building intelligent in terms of all these services, HVAC, access, right, security, fire, lighting, and then you have energy management. Okay. And you can see communication devices, servers, processors, communication to remote devices. You can remotely access, monitor, right? You don't have to be in the building, not necessary, thanks to internet and cloud computing services. Today, energy manager doesn't have to be in the building. All right. If no questions, I would like to wind up. Situmani, over to you.
Hello, sir.
Yes.
Okay, sir. Thank you. Thank you very much, sir. And thank you very much for the participants as well. Have a good night. Let's meet again tomorrow. Good night.